So we've seen how we can use the periodic table, specifically a trend of the periodic table, to help predict the number of valence electrons for a main group element. The number of valence electrons for a main group element is equal to its group number. We're now going to investigate some other predictive properties of the periodic table, some periodic trends that you should be familiar with in using when dealing with concepts in this chapter and throughout this course. The first periodic trend we're going to talk about is sort of lumps these two concepts together of the energies associated with atomic orbitals and linking that to this topic, this concept of effective nuclear charge. So we know that atomic orbitals, as their principal quantum number increases, that their energy increases with regards to s and p electrons for that element. So for example, in sodium, the 1s orbital is of lower energy than the 2s, so on and so forth. But what about comparing a 1s orbital from sodium to a 1s element from magnesium or from aluminum? Well, it turns out that elements in the upper right hand of the periodic table have energy orbitals that are lower energy than those in the lower left. So for example, sodium, which is found right here, has an energy orbital that is higher than something like argon, which is over on the right-hand side of the periodic table. So the fact that all 1s orbitals or all 2s orbitals are not created equal with regards to their energy can be explained by this concept of effective nuclear charge, which explains the charge or the pull that an electron feels when it's in an atom. That effective nuclear charge is termed ZEFF, or sometimes some books call it Z star. MindTap also calls it Z star. This effective nuclear charge can actually be calculated for a particular element. We're not going to do that. MindTap doesn't do that. We're not going to do that in this course. But the effective nuclear charge for an electron is a combination of forces that that particular electron feels in the atom. Specifically, when dealing with outer electrons that are in the outer shell of an atom, they experience something called a shielding effect, meaning that that outer electron has repulsion between inner electrons and that outer electron, along with being attracted to the positive charge that is present in the nucleus due to the presence of protons. So because of that shielding that happens between inner and outer electrons, that outer electron feels less of a positive charge pull towards the nucleus, and thereby the energy of those orbitals is less. So as I said, you can actually calculate effective nuclear charge. We used to do it in previous texts. We're not going to do it. MindTap doesn't do that. They just introduced this concept of effective nuclear charge. So aside from knowing what effective nuclear charge means, you should know the periodic trend for Z star or ZFF, which is that substances that have higher effective nuclear charges, those electrons are held more tightly, and that Z star or effective nuclear charge increases traveling from left to right across the periodic table, but it remains essentially the same in a group with regards to effective nuclear charge. And the reason why we introduce this concept now is because those strong attractive forces make orbitals more stable and with lower energy. So know the concept of effective nuclear charge and know its periodic trend. In the next videos, we're going to be introducing concepts of ionization energy, atomic size, and electron affinity.